Hello everyone, welcome to Brain Blitz Audios. Today in this episode of Derivations, we'll be looking at the 9th chapter in the grade 12 syllabus for physics in CBSE. The name of this chapter is Ray Optics and Optical Instruments. So in this chapter we'll be looking at light as a ray, and this is one of the two chapters which constitute the unit of optics in grade 12. So there are quite some important formulae in here, and today we'll be looking at 3 of them. Our first derivation is to find the expression for refraction of light at a spherical surface. So over here we're going to take the example of a convex surface. So we consider a convex surface, let's say xy, separating two transparent media of refractive index n1 and n2. Now O is the object, the point object present in medium n1 on the principal axis, and I is the image of O formed on the other side. So if we want to draw a diagram for the same, you have a convex surface and you have a principal axis, then you have the object O. You can draw a light ray at an angle alpha, which will be incident at the point M, and over here you can draw the radius of curvature. So the normal will be hitting the principal axis at the center of curvature C, and it will be at an angle of beta, and let's write down the length MC as R, and over here you have an angle called as the angle of incidence, and then the light ray here gets refracted because it comes to another medium. So it slows down and then it changes its angle, and now it hits the principal axis at an image I, and the angle at which it makes with the incident with the principal axis is theta. So this is n1, medium n1, and this is medium n2. So the distance between O and C is u, and the distance O and the pole P is u, and the distance between P and I will be v, and the distance between P and C can be taken as r. Now we have all of these points in this diagram. So now let's consider one of the triangles present, which is triangle OMP. So in triangle OMP, tan alpha, which is equal to alpha for small angles, can be written down as MP divided by OP, the opposite side by the adjacent side. So triangle OMP, tan alpha will be MP divided by OP. So the angle alpha equals MP by OP. Now, same way, if we take another triangle, in this case triangle PCM, so PCM will be the triangle made by the radii, the radius of curvature, the normal axis and the principal axis. So that is the triangle that is made. So over here you can find out tan beta another angle, tan beta, which is approximately equal to beta for small angles, can be equated to the ratio PM divided by PC, where PM is the distance between P and M, the 2 points on the refracting surface, and PC is the adjacent side, which is the radius. So PM by PC is equal to the angle beta. And then the last triangle, triangle PMI, you can consider tan theta, which is approximately equal to theta for small angles, can be written down as PM divided by PI. So over here the image is at a longer distance, so PI is longer, so that's why there's a difference. So PM by PI is equal to the angle theta. Now let's take a different triangle. This triangle is triangle OMC. So if we take triangle OMC, the angle of incidence will be equal to angle alpha plus angle beta. Now this is by using the external angle property of the triangle. And similarly, so now that we've got angle I equals angle alpha plus angle beta, we can write down angle I as equal to PM by PO plus PM by PC. We consider this as equation number 1. Now in triangle IMC, the angle beta will be equal to the angle R plus angle theta. This is again using external angle property of a triangle. So over here we need to find this equation in terms of angle R. So angle R equals angle beta minus angle theta, which will be equal to PM by PC minus PM by PI. Let's consider this as equation number 2. Now, one of the most important laws in refraction is Snell's law. It says that the sine of angle of incidence divided by the sine of angle of refraction will be equal to the refractive index. So sine I divided by sine R equals N2 divided by N1. So since angles I and R are small, so since angle I and angle R are small angles, sine I equals I and sine R equals R. So therefore what we get is angle I divided by angle R equals N2 divided by N1. So now let's cross multiply them. So what you get is N1 times angle I equals N2 times angle R. So now we can substitute the values for angle I and angle R. According to the equation 1, angle I is PM by PO plus PM by PC, and angle R will be equal to PM by PC plus, instead of plus it's minus, minus PM by PI. So now what we're going to do is we're going to take the common term PM outside and we're going to multiply N1 inside. So PM times N1 by PO plus N1 by PC equals PM times N2 by PC minus N2 by PI. So over here you can cancel out PM, and then you can rearrange this to read N1 by PO plus N2 by PC equals, N1 by PO plus N2 by PI equals N2 by PC minus N1 by PC. So now the distance PO is written as U, that is the object distance, but since it's on the other side, according to the new Cartesian sign, you'll be writing that as minus U, plus N2 divided by PI is image distance, that is V, and then N2 minus N1 divided by PC will be the radius of the refracting surface. So therefore N2 minus N1 divided by R. So what we get is N2 by V minus N1 by U equals N2 minus N1 divided by R. So this is the final equation with respect to refraction at a spherical surface. Now let's look at another important formula, another important derivation. We need to derive the expression for focal length of a spherical lens using the lens maker's formula. So you need to derive the expression for the lens maker's formula. So what we're going to do is we're going to consider a point object O placed on the principal axis placed on the principal axis of a convex lens. So over here the image formation will have two steps. Now let's draw the diagram first. So you have a convex lens, which we can write as A, B, C, D. The reason why we write that is that there is an optical axis which is passing through the optical center. So we have the medium outside is N1, and here the medium is N2 inside the lens. So suppose we have an object O, and then the object refracts to the first part of the refracting surface, so it will usually form an image I1 here. But since we have another refracting surface adjacent to it, so it will refract even further to form the image I. So the image I is formed somewhere here. Now note that this diagram is rough, so there might be some problems in it. So this is the image distance U. The object distance U. And then this is the image distance, final image distance V. And for the earlier case, the image distance V1. So there are two steps here. Step number one is the first refracting surface. The first refracting surface forms image I1, and number two, image I1 acts as virtual object for the second refracting surface. To form image I at a distance V, where V is the final image distance. Now remember that we derived the formula N2 by V minus N1 by U equals N2 minus N1 divided by R. So we're going to use this basic formula in two steps. So for refraction at ABC, the formula which we will use is N2 by V1 minus N1 by U equals N2 minus N1 divided by R1. So basically, the surfaces, this curved surface ABC has a radius R1, ADC has a radius R2, and the medium which is enclosed by the two refracting surfaces is N2, and outside the medium is N1. So at ABC, we're going to use the formula for refraction due to a spherical surface, and over here the object distance is U, the image distance is V1, and the radius is R1. Let's take this as equation number 1. Now for the other side, for refraction at the refracting surface ADC, there is a slight change. The formula now becomes N2 by V minus N1 by V1 equals, it's actually N1 by V minus N2 by V1 equals N1 minus N2 divided by R2. So the reason why that happened is that at the second refracting surface, the image I1 acts as the object. So V1 now becomes the object distance. And the final medium where the actual image is formed is N1. And the medium where I1 acted as the virtual object is for the medium N2. And that's why it becomes N1 by V minus N2 by V1. Now what we're going to do is we're going to add equation 1 and equation 2. So now what we get is N2 by V1 minus N2 by V1 minus N1 by U plus N2 by V1 minus N1 by U plus N2 by V1 minus N2. Okay, so it's basically N2 by V1 minus N2 by V1 minus N1 by U plus N1 divided by V. And on the right hand side, it's N2 minus N1 divided by R1 plus N1 minus N2 divided by R2. So as you can see, N2 by V1 cancels itself because there is addition and subtraction. So therefore what happens is that the left hand side will become N1 by V minus N1 by U, and on the right hand side what we're going to do is we're going to take N2 minus N1 as common. So N1 minus N2 can be written as minus of N2 minus N1. So therefore we're going to get N2 minus N1 times 1 by R1 minus 1 by R2. So now what we're going to do is we're going to take N1 common from here. So N1 times 1 by V minus 1 by U equals N2 minus N1 times 1 by R1 minus 1 by R2. So 1 by V minus 1 by U can be written as N2 by N1 minus 1, and then over here it can be 1 by R1 minus 1 by R2. So that means you have 1 by V minus 1 by U equals N21 minus 1, that is refractive index of 2 with respect to 1 by R1 minus 1 by R2. So this is a formula that is quite close to the lens formula, the lens maker's formula, but what we're going to do is we consider V equals F and U equals infinity. So therefore you have 1 by F equals N2 1 minus 1 times 1 by R1 minus 1 by R2. So this is the actual lens maker's formula. But do we stop here? No, because this question can be twisted to get some more values. You can also use the same derivation in order to find the lens formula. So remember, when we're doing it for the lens formula, we consider this as equation 3, and we consider the lens maker's formula as equation 4. So now what we do is from equation 3 and equation 4, you'll get 1 by f equals 1 by v minus 1 by u. So you get the lens formula as well. So this question is used to both find the lens maker's formula as well as the lens formula. And for the lens formula, you'll have magnification as p by u. That will be the same as n1 by n naught. So that is obvious. So that's how you prove the equation to derive the expression for both the lens maker's formula and the lens formula. Both formulas are important. The lens maker's formula allows you to calculate the focal length with respect to the media and the radius of curvature, and the lens formula is what we normally use to find focal length when the image distance and object distance are given. Now the final derivation here is to find the expression for refraction through a prism. Now what we're going to do is we're going to consider a refractive prism ABC, where AB and AC are the refractive surfaces. So that means BC will become the base. When we draw a prism, so this is most likely a triangular prism. So we have A, B, and C. So we will have an incident ray I. So then what happens is that we take the normal, and then you get a refractive ray R, and then over here you draw another normal, and you find out that the refracted ray now emerges out of the prism, so we call this the emergent ray. So this will be angle I, this will be angle R1, this will be angle R2, and this will be the angle of emergence E. So this is normal 1 and this is normal 2. So this angle in this prism is called the angle of prism, which is angle A. And when you extend the angle of incidence and the angle of emergence, you get an angle here that is angle D, angle of deviation. So now let angle A be the angle of prism, and PQ is the incident ray, QR be the refracted ray, and RS be the emergent ray, and angle I be the angle of incidence, angle R be the angle R1 and angle R2 be the angles of refraction, and angle E be the angle of emergence. So we take this as P, we take this point Q, this point is R, and the emergent ray point is S. So that settles the diagram. So in the diagram we have a quadrilateral. So the quadrilateral is present as QMRN. So in quadrilateral, QM Rn. The opposite angles are equal to 180 degrees. So the sum of the opposite angles, that is R1 and R2, will be equal to 180 degrees. The other, okay, so here the quadrilateral is not QMRN, it is QARN. So either way, you have angle R1 as the angle R1, and angle R2 will be the angles of refraction. So R1 plus R2 is equal to 180 degrees. So therefore, you can imply that angle A plus angle N will also be equal to 180 degrees. Angle N is the area where the normal, the angle at the point where both the normals interact. So they form an angle, angle N. So now let's take triangle QNR. So in triangle QNR, angle R1 plus angle R2 plus angle N equals 180 degrees. So that means QRN, which is the angle that's formed below the refracted ray. The triangle that's formed below the refracted ray has the angles R1, R2, and N. Their sum will be equal to 180 degrees because the sum of angles in a triangle. So let's consider angle A plus angle N as equation 1, and we'll consider angle R1 plus angle R2 plus angle N equals 180 degrees. So that is number 2, equation number 2. So from 1 and 2, you get angle A equals angle R1 plus angle R2. Because in equation 1, angle A plus angle N gives you 180 degrees. In equation 2, you have the sum of Q1, the sum of R1 and R2 plus N giving you 180 degrees. So angle A will be equal to angle R1 plus angle R2. So now we consider this equation as equation number 3. Now next we consider triangle QRM. So in triangle QRM, angle MQR equals angle I minus R1, and angle MRQ gives you angle E minus angle R2. So M here would refer to the point where the incident ray and emergent ray meet. So there the angles are the difference between the incident angle of incidence and the angle of refraction, and angle of emergence and angle of refraction. So that's what we wrote. So vertically opposite angles gives you the same. So now using exterior angle property, we get the angle of deviation as angle I minus R1 plus angle E minus R2. So here we can write it as angle I plus angle E minus the sum of R1 and R2. So therefore angle D will be equal to angle I plus angle E minus angle A, because the angle of prism will be the sum of the angles of refraction. So therefore you get angle A plus angle D equals angle I plus angle E. We consider this as equation number 4. Now angle D is referred to as the angle of deviation. If we increase the angle of incidence, angle of deviation decreases and reaches a minimum value, and then it starts to increase. So at minimum deviation, we have angle I equals angle E. So therefore angle R1 equals angle R2, and they become a common angle R. And let's take delta as the minimum angle of deviation. So angle A can be written as 2 times of angle R. So therefore angle R can be written as angle A divided by 2. So now we substitute these values in equation 4. So when we substitute them, you get 2 times the angle of incidence, so that is angle I plus angle I, so that is 2 times angle I equals angle A plus angle delta, where delta is the angle of minimum deviation. So angle I equals angle A plus angle delta divided by 2. So that is how we find the incident angle when you have the angle of minimum deviation given. You can also use this to find the angle of minimum deviation when the angle of incidence and the angle of prism is given. So by Snell's law, we can also find out the refractive index here. So that is sine I by sine R. So sine I will be equal to sine of A plus delta by 2, and sine R will be same as sine of A by 2. So this will be the refractive index of medium 2 with respect to medium 1 in a prism at minimum deviation. So you can also find the refractive indices of the media if the angle of deviation, the angle of prism is given. So these formulas are very, very important, and that's why this derivation is extremely important as well. So we hope you found this video interesting and informative. For more of our useful and interesting content, don't forget to subscribe to our channel, which is Brain Blitz Audios. So until the next webisode, take care, stay safe, bye-bye for now.